Hey everybody, welcome to episode 19 here of Bennett's Chemistry 12 tutorials. We're continuing in the titration unit, so this is the second class of titration. First class was more of a general kind of understanding of the fact that titration is a technique, what equipment you use, how it applies to acid-base reactions, a little bit of the introduction to the concept of the stoichiometry of it, and some of the fundamental stuff. So it was a very introductory class. Today we're going to start getting a little bit more into the nitty-gritty of titration, some of the subtleties and complexities that will go above and beyond what you've learned previously about titration. So if you did happen to get the opportunity to do some in Chemistry 11, this is going to add layers on what you already know. Okay. Today's class, if you can see over my shoulder, today's class is about indicator choice and titration type, and that in and of itself might actually create a little bit of a question mark in your brain. What do you mean indicator choice and titration type? I thought there was one type of titration and only one type of titration. If we're doing an acid-base titration, isn't there just an acid-base titration? And who cares what the indicator was? The indicator just changes pH or changes color, at pH of 7. Isn't that all that we need to know? And the choice doesn't really matter. All of what I just said is not really true. So what you've learned previously about titrations is based upon a whole bunch of assumptions, and some of those assumptions were based on the fact that every acid and every base were all kind of the same quality. You didn't know about strengths, as it were. Okay, and so from the acid-base unit, you've learned that there are strong versus weak, both acids and bases within those categories. And so what happens is the fact that you've got different strengths of acids and different strengths of bases leads to some abnormal situations that you didn't previously know. And so you can't throw a blanket statement over acid-base titrations because you're not talking about apples to apples here. Okay, you can't consider a weak acid and a strong acid as the same thing. Okay, so there are several things we need to walk through here again. And so we get a little bit more mathematical, but not tons. We're not actually doing titration calculations. You can see kind of down here in the green that the next class is going to start into the calculation part. So you do a titration, you get some numbers from it. What does the calculation look like? What types of calculations are we doing? Okay, so we'll go through, and the first question that I've got up there is, why is there even a need for different indicators? Like, where is that coming from? Like, indicator choice. Why do we need to have a choice? And what are we choosing between? So, and that's a much more complex answer than just something simple. There needs to be an explanation, and in Chem 12, the expectation is you know all the why of these things, not just, okay, so if you've got this and this, you must use this indicator. Of course, that is an important thing to kind of have in your brain too. However, you're expected to know why. And so this lecture is going to be about the why. Okay? So let's go through this first concept of why is there even a need for different types of indicators? Okay, so let's go back, and I've done this drawing that I've drawn here is nowhere near as good as the one that I did on the last lecture. So you've got a burette. Inside the burette, you've got a solution, and it's either acid or base, one of the two. And I'm going to introduce a word here. The word is standardized solution. We'll get it when we do the calculation stuff. I'll explain standardized a little bit more. Standardized just means it's of known concentration. And it's known concentration because it has been made by the experimenter. Okay, so you've kind of made it from scratch, and so when you make something from scratch, you know exactly what's in it, and since you've measured all the quantities, you would know something like its concentration. So it's standardized, and there's some more to that. It's a more complicated story than just what I just said there, but we'll come back to that when we do the calculations. So you start with a burette, and it's hanging like it's clamped on with a burette clamp, and that's attached to some apparatus so that it's hands off. And down below you've got an Erlenmeyer flask, and the Erlenmeyer flask will be filled with whatever solution you're trying to test. Okay, whatever you're trying to find out. So if I put base up here and it's a standardized base solution, I'd probably be testing an acid with some unknown quantity to it, whether it's an identity or a concentration or percent composition or whatever down there. Okay? One of the critical components of a titration is when you mix these two things, you're going until you hit the equivalence point. Okay, so the equivalence point being that point where stoichiometrically the acid and the base have perfectly reacted and you have no excess of either one of them, right? And so the burette allows you, because it's got a very kind of sensitive valve on it, you can control it drop by drop, and you can actually stop the addition of one reactant to the other whenever you want in a controlled fashion. So when you get to that equivalence point, or in that neighborhood for lack of skill or precision, really, it's not necessarily skill, it's more precision. You'll be really close to it. You'll never hit it perfectly, but you'll be really close to it. But we're going to that equivalence point. And one of the concerns is, how do you know you've hit the equivalence point? Like, what is your indication that you've hit the equivalence point? And the indication is going to be from a change in pH, okay? And a change in pH is very critical here, because if I've got base up here in the burette and I've got acid down here, when I mix those two things, they're going to use each other up in a neutralization reaction. And when they've perfectly reacted, so you've reached that equivalence point or stoichiometric point, you have zero excess of either one of them. And that should be indicated by a pH, a very specific pH, because the acid and the base has been removed. And all you've done is you've produced the products of the neutralization. So essentially, when you reach the equivalence point of an acid-base titration, you have a solution of whatever the products were. And that's very critical that you understand that concept. Now, when you've reached that point, it will be associated with a very specific pH. Notice I haven't said 7, because it's not always 7, as we're going to get to. But the products of the titration will be associated with a very specific pH. And it's that pH that we want to have some indication that, oh, we've reached our equivalence point. You can't see a pH. You can't tell, no one in this world, at least I don't think so, and that'd be a very strange superpower, to be able to look at a solution and say that's pH whatever. Okay, I mean, a pH of hydrochloric acid with a pH of 0 sitting beside a beaker of water with a pH of 7, they don't look any different, right? They're clear and colorless. You can't tell them visually that they're different. So you're not going to be able to spot a pH change unless you've got an indicator in the solution. And indicators are chemicals that change their color. I mean, really what happens is they change their structure at very specific pHs. And when they change their structure, they change the different wavelengths of light that they absorb. And so they change color. And it's that color change that you're going to observe. Okay? And will indicate to you when you've reached that very specific pH that you're expecting in your titration. So that is our indication that we've reached our equivalence point, as a specific pH change at a very specific point. We need an indicator that will change color at that expected point. So you might be asking the question, I mean, hopefully you're asking that very logical question, why isn't it always just 7? Shouldn't we always just be looking for an indicator that changes color at pH of 7? And the answer is no. And the reason why has to do with that concept of when you do a titration, you have zero of the acid and the base on the reactant side. They're used up. Okay, so you have to theoretically, at equivalence, you've got zero of those things. They've been used up. You have a solution of the products, and that is critical, that you understand you have a solution of the products. Well, the products aren't always going to be neutral things. And that's kind of where the philosophy comes from. Okay? So, what I'm going to do is I'm going to walk through 3 different scenarios here. And in each scenario, I'm going to show you kind of the concept of if I was doing a titration of this category, this is what I would expect. Okay, I won't be talking about specific pHs. I'll be talking about ranges. And you'll notice over here, when you look at the blue starred things here, where what should you walk away with? What knowledge should you have when you walk away from here? There's the conversation about ranges, acidic, basing, neutral ranges. There's no conversation over here of a very specific number. It's usually a range. Okay, so we're going to be talking about acidic, basic, neutral ranges of things. Okay, so let's go into why there's a need for different indicators, kind of where the chemistry is coming from, or what the chemistry is telling us to get to that point. So here's our basic setup. So 3 scenarios. First scenario is when I take a strong acid and strong base and I'm titrating using one or the other being the standardized solution. It doesn't matter. If the mixture is a strong mixture, and actually we call it a strong titration. You'll actually hear chemistry people talk about a strong titration. So when you're talking strong, that means a strong acid and a strong base. Which is which, like which one's in the burette and which one's in the Erlenmeyer, doesn't matter. Okay? The reason why it doesn't matter is because you're mixing them, they eventually come together and mix with each other. Okay? So you can pick your favorite strong acid and your favorite strong base. Okay? So I'm going to go with monoprotic things. So the one that I'm going to use, and I don't want to use the very typical one, the one that people always use. I'm going to use strong acid of nitric. Okay, so nitric acid is monoprotic. It's one of our 6 strong acids, and it's monoprotic. With potassium hydroxide. So, it doesn't matter which goes where. So let's pretend that the hydrochloric acid is down in the Erlenmeyer flask. Okay, so it's I've got a sample of hydrochloric acid down there. And in the burette, I've got the potassium hydroxide. And let's pretend we have standardized the potassium hydroxide. So we know exactly what its concentration is, and we're adding it into the hydrochloric acid to find, let's say, the concentration of hydrochloric acid. So we're doing this titration. I'm not going to worry about numbers or anything. That's not what we're doing today. We're talking about qualitatively here. But when I react these 2 things, okay, so pretend I've got a 10 milliliter sample of hydrochloric acid down, or HNO3 solution down below. And I start dripping in the KOH. Okay, so as I'm dripping it in, the KOH that I add reacts 100% with the HNO3. They're both strong. This thing goes like a bat out of hell is what I want to say. So it goes very strongly, 100%. Into what products? Okay, so what does it make? Well, the hydroxide from the base and the H from the acid, they come together and they form water. Okay, and then you make a salt. Remember the whole acid plus base makes water and a salt? Well, when you're doing a strong titration, that little saying you had that you first probably had in your head in Science 10 is when you learn the different types of reactions. So a neutralization, you're really talking about a strong mixture. Okay, so water and a salt. Well, how did you get the salt? Well, it would be the cation that comes from the base and the anion that's with the acid. So the cation from the base is potassium, is +1. The anion from the base is NO3 -1. So the salt that you make is KNO3. And that's a formula equation, and it's probably pretty darn typical of what you've learned from the first moment you started acids and bases in science, whatever, science 10 probably, all the way to this point. Okay, this is kind of what you've learned. Now, remember what I said. The whole indicator choice thing and all that kind of stuff is based on what you have made at equivalence. And so your understanding of this is a critical thing. So when you're at equivalence, okay, so if I keep dripping in KOH into my HNO3 and I keep dripping it, keep dripping it, keep dripping it, I have hit equivalence when the amount of KOH, the moles of KOH that I've added, I shouldn't say amount, the moles of KOH that I've added exactly equals the moles of the HNO3 that was present in the original solution. Why is it exactly the same? Because they're in a 1-to-1 ratio. And so theoretically, moles of KOH and moles of HNO3 will be the same when I hit equivalence. If that's the case, then I will have, so at equivalence, I will have 0 moles of HNO3, and I will have 0 moles of KOH. I've mixed them. They've chemically reacted 100% into the products. They're gone. They're reacted. It doesn't matter that I'm adding them. They've reacted. Now, if I go 1 drop too much, and I add just an extra little bit of KOH, well, that's no longer 0, because there's no HNO3 to react it. So if I add more KOH, well, then I'm just dumping in extra moles of KOH, and that's no longer 0. I've gone past the equivalence point, which in a titration, you're trying to be skilled enough that you don't do that. So I've done this perfectly, let's pretend. And so you have 0 moles of your acid and your base. Now all you have is you have these things. Of course, how much you make of those things is dependent on how much of this you had to react in the first place, right? So it's not necessarily how much we've made that is critical here, it is what we have made. So we've made water, and we've made a salt coming from the strong acid and the strong base. Okay, this is critical. So at equivalence, you have a solution of the products. The most important thing to understand in this entire lecture is at equivalence, you have a solution of the products. The solution of the products would be water, which is a neutral thing, obviously, and then a solution of KNO3. So then your understanding of hydrolysis automatically kind of pops out. If I've got a solution of KNO3, what is the pH of a solution of KNO3? Forget that it's in titration anymore. You just have a solution of KNO3. Well, KNO3, let's ask ourselves the question, what does it do when you have a solution of KNO3? Well, KNO3 is really dissociated. Like if I said aqueous KNO3, I told you earlier, this is a formula equation. KNO3 is a soluble compound, so really it's not K is attached to NO3s floating around. It's K pluses and NO3 minuses floating around individually doing their own deal. So what is the potassium doing and what is the NO3 doing? And so we go through our flow chart for hydrolysis of what is each thing doing. So the K plus, what is it doing? Can it be a base? It's positively charged. Can it be an acid? Well, it doesn't have an H, and it's not chromium, aluminum, or iron plus 3. So it's not one of our 3 complex metal atoms, or ions, sorry. And so this guy is a spectator. Doesn't do anything. It's floating around. It's there, but it doesn't do anything from an acid-base perspective. Okay, NO3 minus. Okay, so let's go through the NO3 minus. Let's go through our flow chart. Does it have a donatable H? No, it doesn't. So it cannot be an acid. Is it the conjugate of a strong acid? Yes. Yes. We knew it was a strong acid going into this titration, so therefore the NO3 minus is the conjugate of a strong acid, of course. So this guy, it's not an acid, doesn't have an H. It's the conjugate of a strong acid, so therefore it doesn't act as a base. So this guy is also a spectator. Both of the ions that are produced from this type of titration are doing nothing. They're floating around, they're there, but from an acid-base perspective, they're doing nothing. So essentially, you have a solution of a neutral salt. And so the pH at equivalence is neutral. Now, I'm using the word neutral, and then in brackets, I'm going to say 7.0 at 25 degrees Celsius. Okay, so I qualified the 7. So it comes out to a neutral pH at 25 degrees it's a neutral pH, 7 at 25 degrees. Why? Because the ions of the salt were spectators. You will always get spectator ions when you're doing a strong titration. So strong titrations will always have a pH that is neutral when you hit equivalence. So keep that in mind. Strong, neutral pH at equivalence. Okay. Let me erase all of this, actually. Okay, so the second category is going to be, so strong we've done. Well, now we're going to start introducing the concept of weak acid and weak bases. Remember from the first titration video that titrations, you're trying to get 100% reaction all the time. So one of your two things that you're mixing in a titration, you're always trying to make it a strong. So you're 100% of the time, you are trying to use a strong acid or a strong base in your titration. It's typically the one that you know its concentration of. It's usually what you're making the standardized solution using. So you will have a standardized strong acid solution, or you'll have a standardized strong base solution with which you're going to do the titration. It's typically what you do. So if you have an acid solution that you know is a weak acid, you would titrate it using a strong base. And so that's going to be our second category here. So strong base, weak acid, titration. We're going to go through this exact same process. So again, I'll use a typical strong base. So one that you're going to see in the lab all the time is you'll see sodium hydroxide. And we will have a standardized solution of sodium hydroxide, and again, we'll go into how you standardize it. So sodium hydroxide, let's see, what are we titrating? Let's titrate a solution of, well, why don't we do the really typical one? So if you titrate acetic acid, so vinegar. So vinegar is just acetic acid dissolved in water. So you can have different concentrations, obviously, but acetic acid, let's use that. That's pretty typical weak acid. So CH3COOH. Now you'll notice I'm not getting hung up on where do I write the acid and the base. It doesn't matter which order you write them in. It doesn't matter. It's just how you put it on the board. It's not that big of a deal. So the fact that I'm using sodium hydroxide, though, means that this reaction is going to go 100% towards the products. Okay, regardless of the fact that I've got a weak acid. The sodium hydroxide forces it to go. So this is going to go 100%. And again, This is an acid-base titration. Okay, so the H from the acid will stick on to whatever the base part is. Well, sodium hydroxide, the base part is the hydroxide itself. So the acid part of acetic acid is the H at the end of the Q, okay, which is, it's an organic acid. So the H at the end there is going to attach with the hydroxide from the base, and it's going to make water. And then you will make a salt with the cation from the base and the anion from the acid. So you're making sodium plus 1 with acetate, CH3COO minus. While the compound of sodium acetate is written as NaHC3COO. Interestingly, a lot of people will actually keep that organic notation, and they'll actually write the Na at the end. So they'll write CH3COO Na, indicating this is where the cation is attached to, which is fine. I mean, you'll see it, so don't be freaked out when you see it kind of in that format. Okay, following the same concept, that if we arrive at equivalence, this is a 100% reaction. So whatever moles of CH3COOH were in there, regardless of the fact that it was a weak acid, so even if it was in an equilibrium, if you've got some CH3COOH and you add some NaOH, what you're going to do is you're going to react away all of the acetic acid. Okay, that's what you're going to do. You're going to react it away. So you keep adding sodium hydroxide until the CH3COOH disappears. Now, some of you may be thinking, and that's fine if you are, because it's not incorrect. I don't want to lose some people here. But CH3COOH is part of an equilibrium. So you've got components of that weak acid equilibrium floating around in the solution. When you add some NaOH and you remove some CH3COOH, you're removing part of that equilibrium. And so there's a Le Chatelier shift to replace it. Okay, so you're kind of side reacting it with the NaOH. So what will happen is the CH3COOH, that equilibrium, will continue to produce CH3COOH until that equilibrium's all disappeared. Okay, that's kind of digging really deep into that concept. From a titration perspective, whatever moles of this thing were originally in the solution when you first made the acetic acid solution, or whoever made it, those moles are going to be reacted by the moles of NaOH. Okay, so at equivalence, those two things again go down to 0 moles. Effectively meaning they're not there anymore, and you have a solution of that. So water, and then you have a solution of sodium acetate. So following that same concept, if you had a solution of sodium acetate, sodium acetate produces sodium ions and acetate ions. Again, this is a formula equation of the neutralization up here. This thing is the formula of sodium acetate, but it's aqueous. It's a soluble ionic compound. So being a soluble ionic compound, it's not really sodium acetate floating around. It's sodium ions floating around and acetate ions floating around. So then what do they do? Do they participate in any acid-base reactions with water, like Bronsted-Lowry reactions? So the sodium can't be a base because it's positively charged. Does it have a hydrogen? No. Is it one of our chromium, aluminum, iron? No. So the sodium is a spectator, does nothing. CH3COOH, does it have a donatable H? No, those H's right there are not donatable. So it can't be an acid, doesn't have a donatable H. Can it be a base? Now, sorry, that was the wrong question. Is it the conjugate of a strong acid? And the answer is no, it's not the conjugate of a strong acid. Because it's not the conjugate of a strong acid, it's the conjugate of a weak acid. CH3COO minus can act as a base. So imagine this from a chronological perspective. these two things are mixed during the titration, right? So these guys chew each other up. They force the formation of those things, whether they like it or not. They get forced to form over here. So you do the titration, bubble, fizz, blah. Well, it doesn't actually bubble and fizz, but imagine they're reacting and they're producing those products. So this almost gets forced to be made. And so you end up with this forced solution at equivalence where you've got sodium being a spectator, but you've got this guy, which is, whoops, let me write that properly. That guy is a base. So you've created a solution of a base, which means you're not expecting a pH of 7 at equivalence. The pH at equivalence is going to be greater than 7.0. It's going to be basic. Now, how much higher than 7? Like, what will the pH of that be? Will it be 8? Will it be 9? Will it be 10? Will it be 11? Like, where is it going to be above 7? That's a complicated question because where would it be depends on a couple of things. It depends on the Kb of the base, which, since we know it's acetate, we can we can calculate the Kb of that base. So we know that. But concentration is another factor that plays into what does the pH of the solution come out to. Think back to all the weak acid, weak base calculations. What you put on the initial line for the IRE kind of made a difference as to what the final pH of that solution was going to be. Because when you start the titration, you don't know how many moles of this thing you have. Prior to doing the titration, you don't know what the exact pH is going to be because you don't know what the concentration of the salt will be at the end of the titration, at equivalence. And because you don't know that exact number, what the concentration is going to be, you can't really pinpoint the exact pH. What you can pinpoint is that it's going to be above 7. That's you're predicting it will be above 7. How far above 7? Well, we can kind of guesstimate a little bit where the majority of these things are going to fall. The majority of them, because generally speaking, we're talking about certain concentrations, right? And we're expecting certain amounts. And you can do some hypothetical calculations if you wanted to try and figure out what that pH is going to be. But for practical purposes, you're not going to spend all that time doing hypothetical calculations just to find that by far the majority of pHs at equivalence, when you're talking about a weak acid being titrated by a strong base, by far the majority are going to fall in the neighborhood of around 8.5 to 10.5, somewhere in that neighborhood. Okay, now you may get one slightly lower than that. You may get one that's slightly higher than that, depending on what the concentration is and what the actual base is that you're using. Therefore, it's Kb. But by far the majority, like 90% of them, are probably going to fall in that range. And so, as long as you know it's supposed to be above 7, you can then choose an indicator that maybe will change color at a pH above 7. And particularly within that range that I just said, somewhere between 8.5 and 10.5, somewhere in that range. So if you can find an indicator that does that, that's awesome, because then you would choose that one. But this is why it's not going to be 7. This is why not all titrations and neutralization reactions make neutral solutions, because the salt doesn't just sit there and do nothing at equivalence. It does something. So then it comes to our third one. You probably already anticipate what you're talking about. So far we've got a strong titration gives you an equivalence of 7, neutral, okay, at 25 degrees. A strong base weak acid will give you an equivalence at pH at equivalence above 7. Okay, so if it's a weak acid, it gives you pH above 7 because of the salt that you're making. If you're titrating a weak acid, it makes a weak base. Therefore, it's above 7. So therefore, what do you anticipate strong acid with weak base is going to make? Okay, you can probably anticipate what that is. So let's go and let's do an example of that. Okay, so we'll go strong acid, weak base, titration. Okay, so let's take a strong acid. Let's go with HCl. Sure, why not? Common one in the lab. Probably have lots of hydrochloric acid kind of kicking around in the lab. So you make a standardized solution of HCl, so you know its concentration, and then you titrate a weak base. Now, weak bases, as long as we have a negative charge and it's not the conjugate of a strong acid, we'll be good to go. So I'm going to throw kind of a weird one in there. I'm going to throw in carbonate. Which is CO3 negative 2. Now, you can't go get a solution of just carbonate, right? Like, there's no such thing. If you can't just get a solution with just the negative ion. It would have a positive cation, enough of them in that solution to balance the charge, because nature doesn't like to have an accumulation of charges in one area. So if I had a solution of CO3 negative 2, it would have come along with a sodium or a potassium or some other cation attached to it. Okay, so chances are this would actually be Na2CO3. Sodium carbonate might be the actual compound that you had in there, but the base would be the CO3 negative 2. Okay, and the sodium is just a spectator floating around doing nothing. So kind of keep that in mind. I'm just kind of cutting to this chase right here. So the HCl, being a strong acid, is going to force this reaction to go 100%, as the other ones do. And what are you going to make? You're going to make, so the H from the acid goes onto the base. What is kind of cool about neutralization reactions is that because they go 100%, the acid and the base keep exchanging protons until there is no space left, right? So every single CO3 negative 2 that's floating around in that water has 2 spots for H's because it's negative 2, which means that to neutralize a single CO3 negative 2, I gotta put 2 H's on it. That means I'm going to need 2 HCl molecules to do it. And so you are going to make H2CO3 is going to be made. When you take the H off of the Cl, you take the H off of the HCl, you're going to leave behind Cl minus. Now, to balance that, it takes 2 of those, and you'll make 2 chlorides. This is such an interesting thing because you use the word neutralization. So the HCl is undergoing a neutralization reaction with the CO3 negative 2. When in what they're doing is they're reacting with each other so that like the base kind of loses its ability to act as a base. So you have neutralized it. You have not made a neutral solution. I mean, look at what you've made here. This really doesn't follow the acid plus base goes to water and a salt. What? Only water anywhere in there. So that whole reaction that you learn, that saying that you learn in Science 10, acid plus makes water and a salt. Well, that really only works when you're talking about that strong base, like an OH compound, takes the H from the acid and makes a water molecule, and then a salt. Well, we've learned that not all bases are hydroxide compounds. CO3 negative 2 is a base. So you have to suspend what that word neutralization truly means. Okay, it doesn't mean making a pH of 7 solution, it means removing whatever acid or base was in that solution. Okay, so neutralizing the CO3 negative 2 means getting rid of it and reacting it to form something. Okay, so having said that, if I'm doing this titration and I add 0.70 moles of this, okay, so I'm dripping the HCl out of the burette this time. And down below I've got the solution of CO3 negative 2. And I'm dripping the HCl, and I go and I go and I go and I go, and I find out when we've reached equivalence, I've added 0.70 moles of HCl. Using stoichiometry in the 2-to-1 ratio, the CO3 negative 2 moles were 0.35, half as many, because it's a 1-to-2 ratio. But the concept's the same. At equivalence, they have used each other up perfectly. You have no excess. So at that point, those are gone. We reacted them 100%. So you are left with a solution of this. Okay? So at equivalence, you have a solution of H2CO3 floating around and Cl minus floating around. Cl minus, I'm going to start with that thing first of all. So Cl minus is an anion. Doesn't have a donatable H, but does have, is the conjugate of a strong acid. Okay, so HCl is strong acid. Cl minus is the conjugate of strong acid. So this guy does not act as an acid nor a base. So it's a spectator ion floating around doing nothing. H2CO3. Well, 1 is not an ion. You'll notice it's not an ion. So we're not really talking about that concept. But H2CO3, it's got H's on the left-hand side. You have made an acid. And anytime you're, a weak acid, I should say. Anytime you are titrating a strong acid and a weak base, you are going to make the conjugate of that weak base. The conjugate of a weak base is a weak acid. And so the acid, therefore, is floating around in solution once you reach equivalence. So the pH at equivalence is less than 7.0. It's acidic. I should write that down. Okay, because you've made H2CO3, you've made the conjugate of that weak base. So, kind of 3 categories of titrations here. Strong strongs. Strong titration will make the products of that titration produce spectator ions only, therefore the solution is neutral at equivalence. If you have a strong base, weak acid, it makes a solution at equivalence of a weak base, the conjugate. And therefore, the pH is going to be greater than 7 at equivalence. When you have a strong acid, weak base titration, you're making the products which have a weak acid. Therefore, the pH at equivalence is going to be below 7. So you've got these 3 categories, depending on what you're doing with your titration. None of which, other than the strong, we can anticipate it'll be exactly pH of 7 at 25. But the other ones, we can't determine the exact pH. We know the range. It's either going to be above 7 or below 7, depending on what it is. And so recognizing, like, when we're doing a titration and we're anticipating, okay, I need to know when I've hit equivalence. Well, if it's a strong that you're doing, if you're taking HNO3 and KOH and you're doing that titration, you're anticipating the pH at equivalence should be 7. You want an indicator that changes color at pH of 7. When you're doing sodium hydroxide with acetic acid, you're anticipating a pH above 7. You need an indicator to tell you when you've reached that pH at equivalence. And when you're doing something like HCl with carbonate, sorry, I forgot what I did, you're anticipating a pH below 7, so therefore you choose an indicator that changes color below 7. So all of those things goes into the why do you need different indicators and what the chemistry associated with it is. So now we need to go on to this second part down here, which takes a little bit of doing as well. Okay, so what I've decided to do is I'm going to go through this fairly quickly because we're already at 45 minutes. Okay, so I think what I've decided I'm going to do is, we're at 45 minutes right now, so I think what I'm going to do is I'm going to separate these two so that the first question up here will be this lecture, and then I'm going to do another one so you don't have to kind of walk through and spend the entire time listening to me on these two topics. So I'll separate them, and I'll come back with another video on this idea of the indicators, because it's actually a little bit more complex. It's going to take a long time to explain this one. So indicators and why they are in different ranges and kind of their chemistry and why they would work and what the typical ones are. So we'll come back and we'll do that in a second lecture, just so that this one doesn't end up being too long. Okay, so we'll see you then for a little bit more specifics on indicator chemistry.